I wanted to take you through my own trajectory in Alzheimer's research and make one key point. Whether it's a disease that we are trying to study or a biological process, there is nothing simple. So being a scientist, I guess it's all about managing and being able to face complexity. So there are two broad ways of addressing complexity. One is called the reductionist approach. So many of us, and you can see that in particular in all politicians of all political parties, they try to take a complex socioeconomic, political crisis, local or international, and reduce it to one small paragraph and convince everybody that what they say is the truth, all the truth and nothing but the truth. They know it all. Bullshit. You know, complexity cannot be reduced to just 3-4 bullet points. The reductionist approach has really done more harm in politics and in science than any other of the human cognitive characteristics. So the message that I got working in practically half a century now from my once I finished medicine until today, you know, one thing I've learned is never to take anybody's view as granted, whether this is a Nobel Prize winner or a committee of the world experts or anything, because usually what they agree on is bullshit. And always keep asking questions. The more you advance, the more questions come, and the more you advance, the more questions come. And in the end, there is some outcomes that prove that this kind of extensive, in-depth, and intense effort to comprehend a complex issue is the one that finally brings solutions. So without any other delay, just one to remind you that you have the privilege of being in a room that was designed by Professor Emilio Battisti, Professor of Architecture at the University of Milan. He did this at no fee because he was inspired with the Institute, so he designed this room, including the acoustics and everything else. Unfortunately, there have been a number of interventions, reductionist interventions, but there is nothing I can do about that. The second is that this podium was designed by an amazing Greek Belgian artist, Raoul Cavadias, who was of the wider family of the poet. And when he saw the podium, actually this also has been changed. When he wanted to design this, he said, look, I'm going to do a completely distorted podium to remind the speakers that there is enough distortion in this room and there is no space for more distortion. So they have to keep their data as clear as possible and as non-distorted as possible. But you know, it's nice to know that two world authorities in their respective sort of field have been responsible for the room that you are all enjoying here. So without any further ado, just to remind you that there are some words that are interchanged: dementia, Alzheimer's disease, and so on and so forth. So basically just to say that dementia is a clinical syndrome. So, you know, cognitive decline, progressive and relentless cognitive decline and memory loss, ultimately affecting the ability of the patient to kind of take care of their own needs, is the syndrome of dementia that may have several routes leading to this final clinical phenotype that may involve several distinct pathways, brain inclusions, and so on and so forth. But ultimately, we know that this is a disease of very old age, like you see later, and people over the age of 75, which is basically not even the mean age of onset is 81. So even from the age of 76, you find that the majority of patients have more than one pathology in the brain. So nothing simple. Alzheimer's is thought to be the commonest form of dementia. We do not have very clear ways of defining what Alzheimer's is, except that in the recent years there has been an international agreement that a biomarker or pathological signature made of abnormal amyloid and tau load in the brain and evidence of neurodegeneration, the so-called ATN formula, is the diagnostic sort of signature of Alzheimer's disease. And I'm going to talk a little bit more about this. And then there are some forms that are related to Parkinson's disease, and there is alpha-synuclein as part of that. TDP-43 encephalopathy is the newest kid in the block, called late limbic predominant age-related TDP encephalopathy. Then we have frontotemporal dementia, which is also in many cases associated with TDP-43 with a slightly younger age of onset. And then the rarer forms of dementia that are due to infectious or other diseases. So if we focus on Alzheimer's disease, just to say a few things, probably you know all of this, but it is a worldwide challenge because of the huge numbers of patients. It's a disease that starts being noticeable in very small numbers at the age of 65, and every 5 years the prevalence doubles. So we end up at about a risk of about 30% plus in anybody who lives over the age of 80. And the mean age of onset in our analysis in the UK is 81.2 years. So it is a disease of the older old. The etiology is complex, resulting from multifactorial interactions between non-modifiable and modifiable factors. It's not a genetic disease, but it has a somewhat high heritability for a complex non-genetic disease. It's now estimated at about 75%. And again, like all complex diseases, we are still far from understanding fully the boundaries and the classification and heterogeneity of Alzheimer's disease. So this is what I was explaining in terms of age. You can see that it's basically here, that at about the age of 80, that numbers become really huge, continue growing, and this is the age of onset in males and females, and you see that it's across the world. There is no change around the world. And basically this slide explains why very few people were worried about Alzheimer's disease 30 years ago, and why now it's becoming a huge socioeconomic and healthcare problem. Because if you see at the beginning of the century, what have I done now? Oh, bueno más cosas. Εντάξει, είμαστε εντάξει. Okay. Well, if you see the beginning of the century, the number of people between 65 and 34 in the United States was smaller than in 2 years ago, the number of people living over the age of 85 in the United States. So you can see how the population of over 85 has grown. And you can imagine that the population of 78 plus has grown considerably since those very small numbers. So that's when Alzheimer's was first discovered. And basically, until these numbers started becoming noticeable, that's when Alzheimer's started becoming a very sort of, what is it? No. So it was in the 90s when we were still working here. Oops, why is that some genetic studies resulted in some identification of certain genes that were involved in certain familiar cases of Alzheimer's disease. And that's another important point that I wanted to make. So up until the late 80s, 90s, the way that genetic studies were carried was that people were trying to understand what the protein was, and from the protein try to find where the gene was and identify mutations in those genes, and coming up with preventative programs for the prevention of these genetic diseases. Because of significant developments in IT technologies and large-scale sort of management of data, we came to the point where it became possible in the late 80s and 90s to leave the protein on its own, go to the whole genome, take a number of families, do the linkage, disequilibrium studies and linkage studies of families with several family members or several other designs, find the gene and the gene mutations that correlated with specific populations of patients. And we ended up with the concept of the so-called reverse genetics, which has since then become the norm. I mean, I don't know of any new genetic study that follows the non-inverse path. It's been since the late 80s a reverse genetics kind of path. So we found all these genes that encoded corresponding proteins and realized that this first gene encoded a protein called beta amyloid, and that the other genes, their products, when cleaved the APP protein, they produce beta amyloid of several species. Initially monomers, oligomers, and then polymers. And it was only one, not mutation, but susceptibility allele in the APOE gene that was found to be associated with Alzheimer's disease, none of the familiar early onset type, but of the commonest late onset development. And it didn't take long, less than a year, to appreciate that these genes that were found there were basically the end product was the key pathological feature found in Alzheimer's disease, amyloid, beta amyloid plaques, or otherwise known as neuritic plaques or amyloid plaques, which are extracellular masses of beta amyloid, inactive beta amyloid, and phospho-tau enclosed and entrapped in intracellular neurofilament tangles. It didn't take long again for people to start using all this information that came out of genetics and establish patterns of how the late onset non-familiar Alzheimer's disease form was developed. So the initial thought was that the first thing to go up was amyloid, followed by tau, atrophy of the brain, and then the clinical symptoms started occurring. Now what we realized, of course, after many years, is that this is not a bad scheme. It's more or less right. And I think the key element to remember is that, number one, by the time a patient with Alzheimer's disease becomes demented, there is so much damage to the brain that nothing can be done. There is no way that you can reverse the damage to the brain of a patient with Alzheimer's disease. It's too late. So we all appreciate that the best of same problem. We all appreciate that the best time of intervention is basically during the period that someone is cognitively healthy, has no symptoms or signs, has no cognitive decline, but goes through this crazy period of pathological accumulation of several phenomena and proteins in the brain. One of the problems is that it's easier to do studies, genetic studies or even clinical trials in patients that you can actually diagnose than doing studies in this space where there is no way to identify who among the cognitively healthy population in the 65 to 85 age range is at high risk or is not at high risk. We do not have markers to say that someone, we do not have markers to say that someone like your father or me is somewhere here or somewhere here. So it's very difficult to put everybody in the same kind of box. So I'm not going to say so much about this, but just to demonstrate that various studies, and this is from the ABLE study in Australia, have shown how having the 8.4 allele and a positive amyloid PET drives the cognitive decline faster and lower compared to someone who is amyloid beta negative and doesn't carry the epsilon 4 allele. So in 2018, based on the information available to us, a group of wise people, mainly from the US, have gathered, invited by NIH and the Alzheimer's Association in the United States. I refused to be part of this group, and decided that how to define Alzheimer's disease and how to classify Alzheimer's disease. And basically, the outcome was that Alzheimer's disease means having the ATN signature. Now, where they went crazy is that they have suggested that the disease starts when the abnormal tau, and evidence of neurodegeneration is present, even if someone is perfectly cognitively healthy. So they define the onset of disease not at the time that the symptoms start occurring, but when someone can have a PET and an MRI scan and found to have abnormal levels of amyloid tau and neurodegeneration. So, and obviously they have attracted huge criticism and not from many different colleagues, including US students. So a few things to remind. Again, this issue of how the majority of patients harbor mixed pathologies and not clear AD pathology. And then against the ideas that our colleagues of 2018 suggested, there have been a number of scientific pieces of evidence, starting with neuropathological studies. So people who are able to test brains of individuals who never had cognitive decline or memory decline, in various ages, they were able to identify significant amounts of amyloid and phospho-tau, neurofilament tangles, in individuals who are perfectly healthy, which is obviously counterintuitive for the initial suggestion. But even more importantly, from longitudinal prospective studies, in addition to ours, there is the Mayo Clinic study. You have in a way that is sensitive and specific, the onset of cognitive decline and dementia. And then clearly, it has been very clearly shown that the lifetime risk of AD in amyloid positive individuals is quite low, even in the older adults. So the ATN, in my mind, is a good diagnostic signature when you have cognitive decline, mild cognitive decline, or severe cognitive decline, otherwise known as dementia, of having Alzheimer's disease. But having these findings in someone who is cognitively healthy is not by itself, it does not have the sensitivity and specificity to suggest that it can be a predictive value for developing Alzheimer's in the future. So if you go to the data coming from Mayo Clinic, and the first and senior author of the ATN paper came from the Mayo Clinic. But if you look at their own data, where they do amyloid and tau PET costing $10,000 each in practically everybody who shows up at Mayo Clinic, you can see that if you look at the various categories, if you look at amyloid positives here and here and here and here, about 56% of people in their own sample over the age of 80 who are perfectly cognitively healthy are amyloid positive. And so in their own classification, all of these patients should have been told that they have Alzheimer's disease, something for which I feel that I cannot support. So how did the industry reacted? Just to remind people that when a pharmaceutical industry decides to launch a program in drug discovery and development, they expect to spend anything around $1.5 billion as a total investment, and 12 years. So anything that comes to the market today or last year, it's been in the making for 10 to 12 years. And it has already costed over $1 million in costs. Now, out of the 100 projects that are initiated in any industry, only 5 or 6 would make it to the very end. So the wastage is huge. And one of my surprises, having been in the industry in the years 2000, 2006, was how lightly some of these decisions are made. So as soon as the information on amyloid and tau came to the surface, the whole of the industry was rushing to develop drugs that would reduce the amyloid, antibodies that would reduce the amyloid, drugs that would inhibit BACE1 and other proteins of cleaving the amyloid precursor protein and not allowing amyloid to desynthesize, and so on and so forth. And of all of these programs, only one has made it to the very end. And you may have all heard last year the announcement by Biogen of basically a biological drug that seems to reduce the amount of amyloid in the brain, but has little, if any, effect in memory and cognition. So they've made a case, political lobbying, so on and so forth, and they got a sort of a conditional approval by the FDA that the drug could be given under surveillance for what is known as market surveillance, so given to many people, but that would be very closely followed. And that was the conditional approval, but they missed to mention one point, that the company was not paying for the drug. Since it was conditionally approved by the FDA, patients were invited to pay $55,000 each for buying the drug, let alone the costs of being followed at Columbia University or Harvard or Mayo Clinic at an additional cost because there is no YESI. So it was not surprising that from June 2021 until I think the last time I've talked to Ron Pedersen at Mayo Clinic, March 2022, only one patient at Mayo Clinic agreed to pay the cost. And to our intrigue, the company has just announced that, you know, guys, we have decided to reduce the cost to $25,000, hoping that things might change. But their problem is that the insurance companies in the US still refuse to kind of cover this kind of cost. So, a complete disaster. Now, when I was in GSK, and that was right before I left GSK, I was trying to make the case to my superiors and the head of R&D and the CEO of the company, that we are dealing with common diseases like type 2 diabetes, cancer, hypertension, bone diseases, and you name them. They are all complex diseases that are inherently multifactorial and are inherently heterogeneous. So unless we are able to disentangle the key phenotype, what we call breast cancer or Alzheimer's disease, into these components, where we know the key pathways that lead to this disease, we would never be able to find solutions for these diseases. And I was making the argument back in 2006 that we should rely very much on epidemiology, on clearly deeply phenotyping every single individual, use as much as possible genetics and epigenetics, expression, omics, imaging, systems biology, bioinformatics. But what was the problem? The problem was that this was not the way industry was thinking. Their understanding of coming up with ideas of how to come up with new drugs is that as we were having a shower, a senior person said, oh, you know, how about this? And the next day asked 2 or 3 of his associates to start doing some search. And the next thing you know, there is $100 million investment from the company in one direction. This kind of thinking was not clearly understood in the industry at that time. The second point to say is that back in 2005-06, we didn't have much of the modern imaging technologies. We didn't have the untargeted proteomics, being able to prosecute 10,000 proteins at a given with one assay. We didn't have metabolomics. We didn't have sequencing, whole genome sequencing, which is basically now available. We had no means to study epigenetics. We could only do some very basic GWAS using SNP association studies, and this was just beginning to emerge as a science. Since then, this concept has been validated mainly in cancer. So the way that many cancers are now diagnosed and treated basically followed this model. And as you know, breast cancer, which 15, 20 years ago, we were classifying breast cancer based on stages. Now there are about 35 different subtypes because of receptors, because of this, because of that. And the more you can define the profile of each patient, then you can design a personalized treatment regime that targets specifically the specific pathways that are related to this patient. And you know what? Cancer, most of the cancer forms are now treatable conditions. I have high blood pressure since the years I was building the institute, probably as a result of all the bullshit I had to put up with the politicians of various parties in Cyprus to get this approved. And I'm 72 and I live normally taking my drugs. The same is now happening with cancer. Cancer for many is a treatable condition. However, in Alzheimer's, we are back where we were 25 years ago. Now, why did I come with this concept? Because I came from the Cyprus Institute of Neurology and Genetics, where our main activity, at least Roulas and my group, back in the 80s and early 90s, was to take our EMG machine, Roulas, the nurse, and Lefteris with the EMG machine, and go around the Cyprus villages in the north and south, I mean the occupied part and the free part of Cyprus, go to Turkey and see patients in villages, Bulgaria, Romania, Greece. I remember running after a bunch of Ρώμας στην Βόρεια Ελλάδα, πίσω από τα παράθυρα να φύγει γιατί φούνταν να δώσουν ένα. Και μπορούσαμε να το Δευτέρι, δηλαδή η Γεωργούλα την νοσοκόμα, να τους έβρουμε να τους μαζέψουμε. Και we've been to Tunisia, Egypt, Jordan, Syria. I mean, the activity that was done from this group was amazing. And the result was that one disease, which by 85 was known as one disease called Lingual muscular dystrophy, which was a known autosomal recessive muscular dystrophy form, and all the families with limb-girdle distribution were diagnosed as having limb-girdle muscular dystrophy. Following our and many others researchers' efforts, resulted in more than 30 different diseases, each with its own gene and its own mutations. So, even more interestingly, you don't even need genetic tests now to identify some of these patients, because typically limb-girdle muscular dystrophy had a distribution of weakness and wasting which was proximal in the shoulders and the thighs. What you see here is that, what you see here is that the distribution of weakness is also in the calf muscles. And this is very typical of a specific form of limb-girdle muscular dystrophy called dysferlinopathy that also affects the legs. So this is what Alzheimer's needs to get to the next phase. And here is the problem. Like I said, we have to deal with this black box that lasts for about 10 to 20 years, so starts around the age of 50, 60, and progressively accumulates pathology. And when you have the first symptoms of cognitive memory, of cognitive decline or memory loss, it's already too late. And by the time dementia becomes clearly established and the person loses her or his ability to function on a daily basis, there is no more brain to treat. And also, back to the basics, it's a nature versus nurture, another problem of nature versus nurture, where you have a high degree of heritability. So the genetic factors, although they are not causative, they contribute to this equation significantly, at 75%. Actually, interesting now, there are, and I'm going to say a few words later, but there have been studies of using a sort of polygenic resource based on enriched GWAS chips that have shown an area under the curve of 0.8 to predict development of Alzheimer's with ATN signature, which is quite high. And you've heard all the rest. So now we also have a number of tools to study all of these phenomena in vivo, not after death, with health studies. Some of you know how much I've tried to convince previous boards that these kind of technologies was a must. One of the reasons I left Cyprus, so that I repeat it, and you should know, is that I was the first to get a grant from the European Union of 1.5 million euros back in 1996. So 8 years before we joined the European Union, to develop the first image-guided neurosurgery department as part of this institute with top-notch radiology. It was approved by the European Union as the first research grant to this island before even the University of Cyprus existed. And some magic hand of an MRI center that had the monopoly at the time managed to convince the then Minister of Health that that was an unacceptable development for Cyprus, and the then government of Cyprus, in 98, I'm not going to say who it is, but you can always find out, under the pressure of the then minister, decided to tell the European Union to take back their money. So this technology is not available here now, but it is available at the German Oncology Center in Limassol. So you have PET, and you can do all sorts of studies for amyloid, tau, and glucose utilization. We have CSF waves, and more recently there is an increasing number of plasma-based assays that kind of indirectly reflect the levels of amyloid, tau, and other metabolites in the brain. So again, my mind would not accept the accepted common wisdom, and I thought that it was crazy to use the ATN signature as they were doing it, as a dichotomous trait. So if you have a mutation in a gene, you either have it or you don't. So it's dichotomous, it's binary. But if you want to establish in a continuous trait where the line draw a line from above which something is abnormal and below which something is normal, it's kind of very difficult, because there is no human being over the age of 70 that doesn't have amyloid and tau in the brain. So how can you tell amyloid positive, tau positive, neurodegeneration positive? And that was my problem with this. And you see, this is the data that we have from the very big ATME study, where they have clinical and clinical Alzheimer's disease. And you see that they decided to set the threshold of amyloid PET at this value of SUVR. All of these are thought to be abnormal. But you see this huge spike right underneath the threshold. So if these groups had another PET 6 months down the road, they could be, most of them could be here. So we've had this question using the ADNI data. This is one of my ex-former postdocs. And if you look at this data clearly, and you look at the evolution over time of the risk of developing Alzheimer's, it's clearly that you can see that those with elevated amyloid, they have the likelihood of them developing Alzheimer's later in life is kind of increased. But what if you start focusing around the area around the threshold? How could this group compare with this group? Let's forget about the extremes. So we did an in silico experiment where we first compared the whole, what ADNI defined as amyloid positive and amyloid negative, and there was clearly a signal. Then we started to close down to this level. There was a reasonable differential signal, but when we got to this level, and even worse to this level, you could not tell the difference between those who are positive and those who are negative. And when we published this, you cannot imagine the letters that were sent to the editor of Alzheimer's and Dementia, which is a journal of an impact factor of 16, against our thoughts. What was then encouraging, of course, is that the next company that started the clinical trial, they decided to have a trial, 2 trials in a trial. So those who were clearly amyloid positive, and those who, following our paper, were in this group. So they had the peri-thresholds in one sub-trial, and clearly above threshold in another. So the message has been received at least by one company. Now what? So what about non-genetic and nothing to do with amyloid tau and neurodegeneration factors? And I think this important paper in 2020, commissioned by Lancet, gives a very kind of comprehensive sort of view based on life course of various factors, but I don't understand why. See? And as you can see, the first thing to say is that it is, we now have sufficient evidence to suggest that 40% of dementia patients can be prevented by intense multi-domain lifestyle intervention affecting some or all of these modifiable factors, and that there are a number of known protective factors, such as healthy diet, high educational attainment, significant physical activity in middle and late life, and mental activity and social activities. So this is now starting to attract a lot of attention. Secondly, we are now starting to have evidence emerging from the Rotterdam study, the Cambridge study, some German studies, and some studies in the US, suggesting that actually both the incidence and prevalence of Alzheimer's disease is falling by up to 25%, which is massive. And we've been trying to think why. Why is the incidence and prevalence falling by a fourth? And the prevailing thought is that compared to a generation ago, we live a much more active, both physically, mentally, socially. We have better drugs to treat hypertension or diabetes, better ways to monitor cardiac disease, and all of this is helping to reduce the individual risk of developing Alzheimer's by about 25%. However, there are so many more people living over the age of 80 and 90 that the total number of people continues to increase. But it would have increased significantly, massively more if we didn't have this phenomenon. So again, this drop of incidence and prevalence is another indirect evidence that modifiable factors may protect and may reduce the individual risk. So, trying to explore some of these issues, in the UK we have this amazing tool of all of the electronic health records of primary care, and you know that the healthcare in the UK is primary care based, are stored in a massive database containing full electronic health records of over 17.5 million UK citizens of all ages. And then there is another electronic health database called HES, so secondary and tertiary health electronic records. And the ONS, the official, the Office of National Statistics, that is a third database. So having this accessible to epidemiological and biostatistical and bioinformatics researchers is an amazing powerhouse for us. And I personally, 3 of my PhD students have been working on this material. Dasit Barina, she finished her PhD a couple of years ago on cancer and dementia and found some very interesting findings that cancer survivors have reduced risk of developing dementia, and we think we know why. I will talk a little bit more on Bang Zeng, that finished his PhD with me last year on diabetes and dementia. And Anita Kulabilagi, who is a psychiatrist, she's having her Viva next week on ethnic variations in dementia risk, because we know that the Indian and Pakistani populations have increased prevalence of cardiovascular disease and type 2 diabetes, and we want to know whether this reflects in a higher risk for Alzheimer's. So I'm only showing you some of the work now and a little bit later of the work that Bank did in hundreds of thousands of patients with type 2 diabetes. You know that HbA1c is like glycemia, but it's a much more reliable index because it is not a measure of at a given time point. It reflects the overall sort of glycemic level, not of instant values, but longer and more reliable. So we found out, Bank found out, I'm presenting his data, it's my PhD student's data, and you can see here that the higher the abnormal levels of HbA1c level, you can see how this affects the risk of dementia, both in in 2 types of different analysis. So here it's just the time-varying levels of hemoglobin A1c, and this is the measure of coefficient of variation of HbA1c. And again, the more the coefficient is higher, the more it appears that the patient is not well disciplined in treating his or her diabetes, because the HbA1c is supposed to be reasonably stable. So what is the key part of my research? And one can argue that it keeps me young or that I'm getting old by the day, is this. It's a study that is not unrelated to Cyprus, because it was conceived whilst the head of neuroscience at Janssen, who whom I used to know personally in 2013, and myself, were swimming at Gornos Beach. And we are having fun over a glass of wine and over a nice fish at a restaurant in Paris. We came up with this idea. So initially we wanted to do a study comparing cognitive tests face-to-face to see which of the cognitive tests can pick up the onset of Alzheimer's first. It lasted for a couple of years, and then we said, oh wait, let's do a massive study that will use all sorts of amyloid PET, functional MRI, quantitative MRI, throw the book. And that started in 2016, and it's still going strong, where we had initially Janssen as funders. Now we also have Merck, Takeda, and even more importantly, Gates Foundation, and we just got funding of another 10 billion pounds for another 2.5 years. So it doesn't seem that I'll be able to retire before I die. But basically, we follow about 410 individuals since then. Initially 3 monthly cognitive tests lasting for 4 hours, clinical exams, taking blood, urine, even hair, and kind of then following them up over 6 months. So to identify these individuals, the company wanted to have an equal number of people who are above the threshold of amyloid positivity and below. The threshold was at about 20% in this population, in this age range. So we had 210 amyloid positives, 210 amyloid negatives, and all of these people were excluded from the study, but we are continue following them up separately because most of them are just below the threshold. And all of these studies are being done. We've just completed a somalogic untargeted proteomic study of up to now. We've done 2 time points, and in 2 years' time we'll do another 2 time points. We have the enriched GWAS. We are doing full plasma and serum, and urine metabolomics, lipidomics. In terms of neuroimaging, we are measuring structural and functional MRI, tau PET, using this newest tau PET ligand. And of course, we have the data of amyloid PET, and we are doing all sorts of plasma-based biomarkers involving amyloid tau and others. All of these people were cognitively healthy at baseline. And what I can tell you is that by year 3, about 10% have already declined. So we are now able to try and find what are the features separating those who have declined and are declining to the rest. And I think this is going to bring us amazing kind of power. I think our study at Imperial is probably one of the 4 or 5 studies of this caliber in the world. The others are the ABLE study, which is a multi-center study in Australia. There is the Harvard Brain Aging study at Harvard. There is the Sterling Johnson's study in Wisconsin, and the Baltimore Brain Health Aging study in Johns Hopkins. This is it. I mean, and hence the interest from a number of funders to support this. I can tell you that up to now, the study's costs, not to Imperial, but also to various imaging centers and so on and so forth, has been of $40 million. And we expect that until the end, it will exceed $55 million. So moving from observational studies to interventions so that you get an idea of where all of this is leading us. There was a trial called FINGER that was first reported in 2015 by a lady called Pelto and her team, who identified people at high risk based on lifestyle, on a lifestyle-based risk score called KITE, and gave them multi-domain lifestyle intervention in areas such as better diet, more physical activity and mental activity and social activities, and they were the people on the active arm were followed much more closer from the point of view of their blood pressure, diabetes, and cardiovascular status. So, not surprisingly, those who were on the placebo arm, meaning that they had received no support, but they knew that they were part of the study, they did quite well. But those on the active arm, they did even better. And what I think is very interesting is that if you look at the data, because those were data published in 2015, now in 2022 we have the 10-year data, but what we see is that not only they have lower risk of developing Alzheimer's, but they have 30% lower risk of developing Alzheimer's, but they also have lower risk of frailty and sarcopenia and problems of mobility. They have significant lower risk of other diseases of old age, including bone diseases, cardiovascular diseases, and cancer. 20% lower risk of hospitalization in age-adjusted analytical studies, and a significant health economical benefits for the society. So, it's not a secret that as I was reaching the age of 70, I decided that rather than wait for Imperial to appoint someone to replace me, I should choose my successor. So I managed to get Pelto, who is and was professor of geriatrics at Karolinska, to join my group as professor of geriatrics. And last January, I managed to get her to become the new head of my unit, so that I can, I know who is going to be running the unit with me. And she and I are now starting what we call FINGER 2 trial, which is combining a very common, very, very cheap drug with multi-domain lifestyle intervention for the prevention of Alzheimer's disease. This is a study that is funded primarily by Gates. So, why metformin? There have been a number of papers suggesting that there is significant insulin resistance in the brain of Alzheimer's patients, and significant issues around cellular signaling, insulin signaling. There were several papers suggesting a pleiotropic anti-age effect of metformin in basic animal studies, and other clinical studies suggested some potential benefit of metformin in dementia prevention. And here is another finding from my PhD student, who did something very, very smart, and I have to say it was his idea, not mine, and I loved it. So he said, to see whether metformin may have an effect to prevent Alzheimer's disease, let's do this following experiment. Let's take 100,000 people who have been diagnosed with type 2 diabetes, but their diabetes was so low that they never have to take any drug. Is that the group on metformin, their HbA1c levels came down, but they have always been much higher than the placebo group. So this is another significant evidence that metformin seems to have an effect on dementia. Unfortunately, wherever I'm presenting this, weeks later, people send me emails and say, you know what, we started metformin now. Should we stay at 500 milligrams or go to 1,000? But I think the key element is that any drug, any new drug that may come out of any pharmaceutical industry, as you see, Biogen was charging £25,000 a year per person, with thousands and thousands of patients. You can imagine how many more thousands and thousands should take it to prevent the disease. We are talking about billions. Metformin in Cyprus costs, I think, 10 cents per drug, per pill. So it's generic. No company owns the right of this drug. And it's cheaper than aspirin. And that's why we are insisting on this drug as the only kind of combination with a lifestyle. Now, we create this model. Typically, drug trials never take into account lifestyle factors. So in this trial has been specifically designed to combine a drug with lifestyle intervention. This is the design of the trial. And it will primarily be at Imperial, where we expect to have around 300 people starting next October. Karolinska in Finland, where the first finger study was initiated. You will soon hear that, and I would say that I'm very proud of the Institute's initiative, that there is an emerging interest from the Cyprus Institute with other parties within Cyprus to build a Cyprus initiative for multi-domain lifestyle interventions and allowing Cyprus to be one of 46 countries that are developing models of dementia prevention around the world these days. So stay tuned, it's going to be a very exciting stage. And then, just before I finish, I wanted to share with you something completely new that we are starting now in London, in our group, and we call it e-fingerprint. So this started with a crazy initiative of the British government, which is part of NIHR, the National Institute of Health Research, which they call Our Future Health. So their plan is to involve all of the so-called BRC hospitals, so university hospitals that receive huge amounts of money from NIHR, from NHS to do research, and genotype over 2 million people at a significant cost to develop with enriched chips. So practically anything between GWAS and sequencing, to develop polygenic risk scores for a variety of non-genetic diseases. And the way they plan to do this is that we are already installing in all of our outpatient departments kiosks where people can look at the information consent form. If they consent, the nurse will take some blood, and their electronic health records will get connected to the study, follow them up over years, and then automatically information will come in from the electronic health records, and it will enrich the number of outcomes. So some of them may develop bone diseases or Alzheimer's or stroke, and we hope that because of the size of the sample, we may be able to come to a model where genotyping might, in midlife, might be predictive of what is to come later in life. So we went to our BRC and say, wait a minute, guys. So if we identify that a significant proportion of these people are at high risk, why don't we do something about it? And we propose this program. So what we propose to do is, if we get to genotype around 110 to 120 or more thousand people, assuming that about 20,000 might be thought to be of high risk, we hope that perhaps half of them will accept to be part of an online virtual finger-type tribe, where we will be collecting a number of information regarding their lifestyle, their comorbidities, and then we'll be providing a personalized virtual guidance on how to improve on their mental, physical activity, diet, and every 6 months ask them to have cognitive tests, again virtually, using a sort of an iPad cognitive tool. The study will take 5 years, and to our delight, we managed to convince John Hardy from UCL, Doug Garland from King's, and John Paul Taylor from Newcastle to join us in a consortium. So this may prove to be a massive study that will start end of 2022 and will go for 5 years. So again, I may be dying on my sitting on my office in London out of old age. But I think it's a very exciting study, and if this is proven to be of value, it's a model that can be applicable in all parts of the world, and it's the cost of running this is minimal because everything is online. So I'm not going to go and analyze and describe this slide that summarizes my own views on what's happening from birth to late life in terms of modifiable factors, what we bring with us at birth, and how the pathological phenomena are produced, and in the end, what's happening in late life between protective and non-protective factors. But coming back to the basics, I think once we are able to prosecute most of these potential mechanisms, and what I've put in red are things that are evolving as we speak quite massively, let alone the senescent cells. Oops. Oh, I couldn't keep my secrets. Inflammation is a key point. Senescent cells, that there are now significant evidence emerging of the role of these cells in many age-related diseases, and there are now senolytic treatments that target these senescent cells. Epigenetic changes. This is a great story on the fragments of APOE4 and how they are neurotoxic, and perhaps this is the key role of APOE4 in Alzheimer's, mitochondrial, insulin, huge issues there, and vascular pathologies. So, and this is a paper that we wrote last year describing the new tools that we have in PET imaging in prosecuting practically every single of the mechanisms that was described above. So this is a paper that is a review paper back in 2020 that you cannot find if you are interested on the topic. And coming back to where I started, our science, it's not about breaking a bone and putting a plaster. We are all dealing with complexity, and the worst way to approach complexity is by the politician's approach, the deductionist approach. The only way to comprehend complexity is to accept that there is this complexity and you need to disentangle, to really go in depth have a lot of white hair, not expect to finish what you start in 6 months. Sometimes it takes much longer. And perhaps when you are dealing with complexity and you have to do a PhD work that would be for 3 or 4 years, unfortunately, you may need to take a small part of the complex issue to at least clarify that part and add your own brick on the emerging world that would be the solution of complex issues. That's how I feel about it. So this is my Imperial team. Again, I cannot but express my thanks to our new collaborators, unexpectedly including John Hardy. But I'm sorry to say that, the Hardy is here with you. And I will finish by showing you a few faces of the initial nucleus. Just prior to moving to this building, we were still at the Macarius Hospital. And you would recognize very interesting individuals there. This guy seems, this is Deltas, who is now in the University of Cyprus, and many others. But I think it's time to also acknowledge that one of the key workers in the field of thalassemia and genetics in Cyprus is someone who was impatient because his desire was to come up with treatments for thalassemia. So although he built the thalassemia lab at the institute, and then he left to go to work to Melbourne, Marina took over and did a wonderful work. And unfortunately, Panos went to Melbourne to work in a group on thalassemia, which was quite an exciting group of drug discovery and development in thalassemia, but cancer caught him prematurely. And I will tell you a story because we are among family. The day he died, I received a call in my office from Panos. And he told me, I know that I'm leaving, and I just wanted to say that you are very close to my heart. So it's something that probably the most σηκώστη την τρίχα μου. Ήταν απίστευτη εμπειρία. Και next day I received the email that he passed away during the night. So I think we need to remember those who have been real pioneers in this institute and were instrumental in building this institute. I'm sorry guys, it's been a very long talk. But I hope you have retained the key element. Everything is complex. Don't be reductionist.